All right, so let's look at a slightly different type of problem. Still, we are in the world of normal random variable and normal distribution. This one says demand for a product we estimated with normal distribution would mean a 100 and a standard deviation of 10. All right, mu is 100, sigma is 10. How many DVDs should be stocked at the beginning of a week so that there's only 5% chance that the store will run out or run short during the week? Well, in this one, it says, you know what? This is one of the very direct applications of probability distributions in operations management and inventory management. Here's a question. I know estimate of demand distribution for a product, and I want to make sure that I only run a very small chance, very small probability of running out of inventory, because customer and service level and customer experience is so important to me. I want to make sure that I only have very small chance that I'm going to have empty shelf. All right. What is that chance? Only 5%. It means, let me phrase it differently. I want to have enough inventory so that there's 95% probability that my customer demand is going to be less than or equal to whatever that inventory I have. I'm looking for that inventory level. All right, here's the problem. How many DVDs should be stocked? I'm looking for inventory level. All right, in this one, probability is given 95% cumulative, right? What value should I have on x-axis? Well, we can do that in Excel. You can do it in Z tables as well, but I'm going to show it in Excel. Well, let me see. What was the average? Average was 100. Sigma is 10, and that is 5%. Okay, so mu sigma. Mu is 100, sigma is 5, and only 5% chance of running short is 5%. All right, it means that there's 95% chance that customer demand will be less than inventory level. The question is, how much inventory should I have? You see that again, probability is given to you. Well, we got to use a different kind of problem. This is sort of an inverse of what we had earlier. We are going to use norm data inv of probability 0.95, comma, mean 100. So they are written right there. All right, comma, standard deviation 5. All right, this is 108.22. Well, you can have 0.22 units, right? So I'm going to round this up to 109. All right, so let's move on. All right. I talked about norm.dist. We talked about norm.inv. Something to keep in mind, we are going to go back and forth slightly between discrete and continuous world. All right, I have a binomial in discrete world, and when I play with this binomial random variable and its shape, it looks like normal. In what situations? Well, look, this is binomial of 70 and 0.6, and this is what it looks like. It looks like sort of bell-shaped normal. I increase n to 150, p is still 0.6. Again, it's a lot more bell shape. I increase n to 300. It is going to be, again, a lot more bell shape. It looks like there's a connection between binomial and normal, right? How can we utilize this? Well, we can utilize this by approximating binomial by normal, all right? But there is a problem. One, when can I do that? If n times p bigger than 5 and n times 1 minus p bigger than 5, you can do that. That's question number 1. Question number 2, what are the parameters of normal? Well, normal has 2 parameters, mu and sigma. Mu of normal is going to be equal to mu of binomial, np, and sigma of normal is going to be equal to sigma of binomial, square root of np times 1 minus p. All right, question number 2, check. Question number 3, well, binomial is discrete. Normal is continuous. How do we switch so easily from discrete to continuous? Well, we gotta do a little bit of adjustment. That adjustment, because we are moving from discrete to continuous world, is known as continuity correction. So if I want to find binomial, that binomial of n of p, probability of binomial of n of p is equal to x, I'm going to go minus 5 to the 0.5 to the left of x and 0.5 to the right of x, so that the length right there is, for that number x, is equal to 1, length of that interval. All right, so x minus 0.5, x plus 0.5. Well, I'm not going to find probability for binomial anymore. It's going to be equal to normal. Normal of what parameters? np, and square root of np times 1 minus p. All right, so this is again, that continuity correction is shown right here as well. I'm going to skip it for the sake of time and move to next distribution, which is exponential.